important events of any program at the Isaac Newton Institute. In this case, it's the program on complex fluids, and it's the Rothschild lecture, which has been given this year by Peter Constantin, now of the University of Princeton, but who from 1985 until 2011 was at the University of Chicago. And he's recently joined the Princeton University to head up the computational applied mathematics program, where he's director. He needs very little introduction. He's known for his work on Navier-Stokes equations and dispersed wave equations and so on. And he's going to give his lecture as being our eminent professor on this program, which is the Rothschild professorship. But I understand that this lecture is also dedicated to the memory of Jerry Marsden, and you say a few words about that.
Okay. So Jerry Marsden was a phenomenal mathematician who was very well known and loved especially by his collaborators because he had this amazing capability in the midst of a collaboration when it gets stuck to give it this jolt of thought that gets it moving again, the problem moving. So this Marsden Memorial Lecture series, this is the third of this in the series. It's given by, as about subjects and by people that Jerry would have liked to have seen. Okay, that's sort of the criteria number one. And it's sponsored by the Pacific Institute for Mathematical Sciences in Vancouver. Okay, so it's going to be continuing. And so, yeah, I will also introduce Peter as one of those other guys who can give the problem the jolt of thought.
Thank you very much. Oh, I have to turn this on first. Excuse me a second. That's okay. So supposedly now it's on. I mean, I don't know if there is a difference for you. So first of all, thank you very much. It's a great pleasure to be here again. I've been here long time ago, and I enjoyed it very much. It was a program on from finite to infinite or something like that, dynamical systems, long time ago. And it is also a great honor to be speaking in Marsden Memorial Lecture. I've known and loved Jerry for many years. We had kind of like a very parallel universes. You will see, I'll mention some of the equations that he loved and he made great contributions to, like the Euler equations and the alpha model or the Kamasa-Holm equations, which Daryl has a little bit something to do with that also. I am really very honored to be one of the speakers. And regarding the instructions that I got about this talk, they were that it should be addressed to a mathematically literate audience, not necessarily experts. Now, there are all kinds of non-experts in this world. There could be people who work mostly on elliptic PDEs as opposed to hyperbolic PDEs. Then there might be people who work on finite groups, and there might be people who work in, I don't know, selling cars. So I would like to try to be intelligible, but I'm afraid that my talk in the end is, as you will see, about a technical subject that I love. And so I will try to make it accessible. And so I will ask a couple of little requests. First of all, I'm going to use the Blackboard to explain some of the notions or concepts. And people who are not too shy should ask me, what is that? And then I can give a little bit of a definition of what it is. So hopefully it will be something that we can do. Because I'm afraid that otherwise it's going to be a little technical. So before I even start, can I ask a show of hands who among you considers or is considered by others as a mathematician? Okay, so I have an excuse. At least I have an excuse, all right? All right, so let's... All right, okay, so that's, maybe I talk to you then. All right, so first of all, this, I will explain some terms. Originally, I was gonna talk about, the title of, I gave recently a talk that was in another group of non-experts. The people were in statistical physics, and there was a Joe Leibowitz meeting like that, and it was really a couple of weeks ago. I called it non-local dissipation, and somebody in the audience told me that all dissipation is non-local. Did I know that? I didn't, actually, I still don't, but, but the main thing is that even there, I thought that the audience was very non-expert, but not very far. So I will define some of the notions. One is non-locality. So linear operators, let's see if this point's right. So a linear operator between spaces of functions is local if the function is 0 in an open set, then it produces 0 in that open set, so the support is diminished. Partial differential operators are local. Most anything else you can think of is not. And in particular, integral operators are not local. And these things appear, for instance, simply by inverting partial differential operators. If you can invert it, let's say that you have some boundary conditions that will allow you to invert it, then you get a non-local operator. Or by modeling non-local phenomena. And here I'm not going to talk. So non-local phenomena are essentially, in my opinion, they're simply local things that move very fast. So the influence is at a time scale that you don't notice, and then it's therefore far. But I'm talking about same-time observation. So I'm not going to talk about non-locality in time, which is a business of delays, and it's very important in many areas. So applications, I put here, it's a little tongue-in-cheek. These things, it's also an example of how mathematics can be applied to many areas. There are many applications, but few equations. So the first 1, 2, 3, 4, 5 things actually can be written essentially one by one equation. And there are some more complicated examples here. So I didn't know about non-local quantum mechanics, but there seem to be books about non-local quantum mechanics. So there. So there are a bunch of applications, and let me give you some examples. But first, let's talk about what dissipation is. So dissipation is simply the property of, for a linear operator, that it decreases some positive energy. Okay, so in the simplest case, you have a Hilbert space, and you have a scalar product denoted UV, so the energy is the L2 norm, or some norm in a Hilbert space, and then the dissipative, the definition is that the quote-unquote heat operator with this generator decreases energy. And the typical examples, for instance, as I said, is L2. And in L2, you can have this L to be the identity. In that case, you're just damping, and things go down. And this is a zero-order operator. Or you can have your favorite diffusion. So you have a heat equation, an honest heat equation, and that decreases the energy. And then you see here that I jump from zero order to second order. And so how about first order? And first order is non-local. So first order, the square root of the Laplacian is already, and this is going to be the non-local dissipation, the simplest one that we're going to talk about. So typical examples, we're going to focus at some point. Yeah, have a time. So I go till like 6, or who's my boss? Okay. So the equations that we're going to deal with look like this. You'll have a linear dissipation that might, in the end, it will be non-local. And you have some nonlinearity. And the examples of the first applications, chemotaxis and galaxies and so forth, are nonlinear Fokker-Planck equations. It's a little bit of a misnomer. Fokker-Planck equation should be linear, but you can live with this. And so they look like this. I have the first part is a heat equation, and then there is a potential divergence. This little g here refers to the fact that I might be on a manifold, and the derivatives would be then covariant derivatives. But other than that, if you don't like that, you can think of regular divergence of f gradient of u, and u is an integral with some kernel. And what kind of application you are in and what kind of properties the system has depend on the kernel. So it's a gradient system, if written just like so, of a generalized free energy. So there is a free energy somewhere, and this is the gradient system. And we're not going to talk about this, but I just wanted to show another form of non-locality. And if you have complex fluids, because this is the topic of the program, this is coupled, I mean, one of them, the models, the kinetic theory for this, is by coupling the system, we have additional independent variables, additional dependent variables. They're coupled, so this is only a piece of the system, and in particular, the gradient system structure is destroyed. But there are other interesting thermodynamic laws, essentially. So there are the other examples I was mentioning, Marsden. So they're Euler equations of incompressible fluids. This is something that will be in the background of what I'm going to talk about. And they are non-local. Here I wrote a rule for the pressure. If you look at this equation by itself, it's an equation for a vector field. And you insist that that vector field is divergence free. And by introducing this pressure and the gradient of the pressure, if you take the divergence of this equation, you get the Laplace of the pressure is the divergence of u dot grad u, provided this thing has divergence free to start with. So you get to invert a Laplacian in order to get P. If you can invert it, depending on boundary conditions, then you have a rule for P that is non-local, and that's why the Euler equations and the Navier-Stokes equations, which are just adding viscous dissipation to them, are non-local because they have this pressure relation. So you have an additive non-local term. And the alpha model that I mentioned also that Daryl invented, and there were lots of works on this, looks like the Euler equation, but now the velocity that you are advecting with is obtained from the thing that you are advecting by inverting another Laplacian or Helmholtz, so you get another non-locality. In addition to the pressure, which is still non-local, you have this non-locality. Okay, so those are our examples. So what are the basic questions? So I'm going to stop a little bit here and discuss just general, what do we do in PDEs? We ask very simple questions, and the first one is existential: do things exist? So you can write many equations that make no sense or that have very few solutions. So you need a functional framework where solutions exist for a short time, and we refer to that as local existence or all-time global existence. And in many areas, in particular, for instance, geometric mechanics or geometry and so forth, people assume lots of smoothness. And the reason for that is going to come soon. I mean, essentially, it's the next slide. So one of the occurrences, important objects that you are interested in, you assume a lot of smoothness, and then you realize that the thing that you are interested in has a corner, has a kink, has a second derivative that is discontinuous, or a first derivative that is discontinuous, and those are the important objects. So the amount of smoothness that you require has to be actually under control, and you shouldn't need infinitely many derivatives, or the 13 derivatives should not really matter that much to you. So there are criteria. The way we work in this arena is essentially, in order to guarantee smoothness, and you'll see an example, you will go and say that I need this amount of control. If I have this amount of control, then from then on, everything is controlled. And the reason why this is not trivial is the following. So essentially, we have three kinds of results. We have local existence results, global existence results, and uniqueness results. And in typical non-trivial equation, you will have different kinds of spaces in which these results are true. The local existence results usually live in very small spaces, meaning lots of requirements. The global existence results live sometimes in very large spaces, and you talk about weak solutions. Uniqueness usually, and the criteria for regularity, this is quote-unquote a meta-theorem, they're the same. So if you want to guarantee that the solutions will turn out to be smooth, you have weak solutions that are really rough, and you want a criterion that guarantees that they're going to be smooth, or you want the criterion that the weak solutions that you're looking at are unique. Typically, although this is not always the case, typically the criterion is the same. So we are stuck in some sense with the smooth solution framework because we don't know how to do uniqueness. I personally would be very happy to have a very wonderful theory of existence of Luray solutions of Navier-Stokes, which are relatively weak solutions, if we knew a famous open problem, uniqueness for a Luray solution. And then you have a very broad class of well-defined evolutions. Unfortunately, that is not really likely to be the case. So then you ask yourself under which conditions you have unique solutions. Turns out that they're exactly the same conditions under which you have also regular solutions. So that's one of the, so there are many little scandals in this thing. One of the scandals, for instance, is that in order to prove uniqueness in the class of smooth solutions for 3D Euler, a very natural class of functions that are C1 alpha, one derivative Hölder continuous. That can be done very easily for Euler equations, but if you have systems that are a little more complicated, have the same structure for existence, the proof of uniqueness is extremely complicated. You have to go Lagrange. So that's something that, if this was a little workshop, I would actually explain this, and I would offer a small prize for the student who does an Eulerian proof of uniqueness. Okay? So I refer to continuity with respect to parameters, in particular dissipation going to zero, viscosity going to zero, and I'll mention a typical problem in the next slide. And log-time behavior, stability of solutions, and attractors. The word attractors I don't think has been mentioned here in 20 years, so it will be mentioned at the end. So I will describe now a typical problem about viscosity going to zero, because in the end I'm going to quote a theorem that we did in the SQG case. So the term is anomalous dissipation of energy. It's an interesting subject. So you have the Navier-Stokes equations, which is a nonlinear equation, and it has a dissipative mechanism through the viscosity, which is nu is a positive number. And there are two ways of talking about this anomalous dissipation. One is simply letting viscosity, so essentially it's a question of behavior at zero viscosity. So the first one is letting nu go to zero first. So in that case, you drop this term formally, and you deal with the Euler equations. So the Euler equations conserve the kinetic energy, the L2 norm of the velocity. And you ask yourself whether or not, or Onsager actually conjectured, that you can have dissipation in an ideal fluid, in a fluid that in principle conserves energy, and it will happen at a threshold of smoothness. So now here's the first time that I need to write something on the blackboard, I think. So for those of you who are not into elliptic PDEs, so I'll talk about CS, where S, for instance, is a number at this point between 0 and 1. And these are functions with S derivatives. And what's a fractional derivative in this particular case? You have a function f, and you form an increment. And you divide, because these are, let's say, x in Rd. You divide by h to the s, and you let h go to 0. And this is a, let's call it, this is a semi-norm. I don't like to write the norm because it's a different dimension. So a function like this, if this number is finite, in other words, I can divide here this increment by h to the s, then the collection of these functions that are bounded and fs finite is called CS. Okay? So the norm there is the sup norm plus this semi-norm, right? But I don't want to write it because I don't like to mix dimensions. So essentially, that's what CS refers to. So functions that have Hölder continuous exponent of 1/3 should be, according to Onsager, there should exist solutions, quote unquote, for which the energy is dissipated at s equals 1/3 or less. And there are two results here. There is a long story started with Greg Aint and Winan and Titi and myself and Duchamp and Robert, and also with Cheskidov, Friedlander, and Schwidkoy. We kind of cleaned the first part, meaning that if you are, this is a technical term, it's a best of space, you don't care, essentially S 1/3. If you are slightly smaller than CS to 1/3, then you conserve energy. And the slightness is really very, very slight. So it's essentially, there are examples in that space in which if you step into that function, and it's not exactly, it's in the best of space, this is for the ellipticians, 1/3 infinity, infinity, then there, at that moment of time, the energy drops. So it's not a solution, it's just a function. You substitute what would happen to the energy at that moment of time. If you are in this space, 1/3 infinity, infinity, not in this, but in a slightly cousin, then the energy would drop at that time. Okay? But it doesn't solve the Onsager conjecture. Examples of rough solutions, dissipative rough solutions, have started with Schaeffer. It's a horrible class of solutions. Schnirelmann went all the way to bounded, but not continuous. And then Delelis and Sekedi, they found a way to produce convex integration and things that have to do with ideas from Nash-Kuiper theorem. They found solutions that are CS. So these are coming from ideas from geometry and convex integration. And the world record is actually a grad student who's graduating now from Princeton and got to 1/5. So there are weak solutions, constructed examples. It's not an initial value problem. They're just simply examples in which you can produce, actually you can prescribe the energy curve. Can go up, down in any direction you want and then become 0. And you can find solutions with regularity 1/5. This says that the notion of weak solution, because you passed with nu to 0 and you're doing an arbitrary integration in time, forward in time, it's too broad. It's too broad. It gives you, actually, parenthetically, this happens also in 2 dimensions. So you can find these animals that do horrible things in 2 dimensions, and for experts, in 2 dimensions, those animals don't arise naturally from nice initial data ever. So the other way of getting to the implicit limit is to take first time to infinity. You have a situation in which the system is like, in a boiler. You are heating the system and waiting for it to reach some sort of a permanent regime, and then take nu to 0. In other words, you're looking at, let's say, higher and higher heating amounts that you are producing in the system. So the limits, as nu goes to 0, there are going to be some form of statistical solutions. So by that I mean, before you take the limit in Reynolds number, or nu to 0, you are going to consider solutions, trajectories, solutions of the Navier-Stokes equations, and you're going to take time averages on these trajectories of various functions of the solution, and you're going to get this way a measure. And in other words, phi goes to this number. And then you can ask yourself what happens in the limit of Reynolds number going to infinity or viscosity going to 0, and then you get some limiting measures. And for instance, the anomalous dissipation of energy would be taking on a trajectory of the Navier-Stokes, take the rate of dissipation of energy, which is this gradient of u square integrated, and times nu. Take time averages, and then letting nu go to 0. This number epsilon was again conjectured by Kolmogorov to be non-zero. Epsilon parameterizes turbulence, so there is something called the Kolmogorov spectrum, and this Kolmogorov spectrum has a constant, has this epsilon and nothing else in it. So epsilon, the positivity of epsilon is crucial for, as assumed in turbulence theory. The assumption of, or the conjecture would be that there are examples or sufficiently many situations in which epsilon is bounded away from 0 as nu goes to 0. And the little scandal is that there are no even upper bounds for epsilon unless you have decaying turbulence. So for decaying turbulence, it is bounded. It's the only one that's bounded. But actually, all the bounds are in terms of kinetic energy, but the kinetic energy is not bounded. So this is a great fun problem, and I'm going to come back to this because we're going to talk about SQG, and in SQG we can prove that it's 0 if we damp. So here is SQG. The rest of the talk is going to be about SQG. So it's a very simple equation. It's just transport, time derivative. This is really transport along characteristics. So u is a divergence-free vector. I'm going to write it down in a second. And what you do is you're putting initially a bump, let's say in 2 dimensions today, and the bump will move by a velocity. And the velocity, however, is created. So it's called an active scalar. I call it an active scalar because the velocity is created by the stuff itself. So u is produced by theta by some operation, and the operation is very simple, linear operation, constant coefficients, but a little tricky. So it will be in the whole space oriented. And R is a Riesz transform rotated. So R is an operator. Let me write it down in Fourier. I think I did. In Fourier space, if you take the function and Fourier transform, R perp is simply you take the wave number, normalize it, and rotate it by 90 degrees. Or in more dimensions, you apply some constant coefficients antisymmetric invertible matrix. So that's all there is to it. So this has a geophysical origin, Charney, actually, and then Held and Swanson, Held is in Princeton, and wrote papers about it as an interesting model with possibilities for blow up. And then Maida and Tabak and myself pointed out some analogies to 3D Euler, and there were some computations about blow up. So here's the motivation. So the Euler equations, incompressible, 3-dimensional, are perhaps the hardest, and I would say one of the most important problems of nonlinear PDEs. So they are vectorial, nonlinear, and non-local. Vectorial because there are 3 components. Nonlinear, you can see it. Non-local because of that pressure thing. And the global regularity versus the problem of whether or not you can start with initial data that are smooth and stay smooth forever. This is a major open problem. It's behind, in some sense, the Clay problem, in the sense that actually this is really the meat of the Clay problem. And it's open. So in order to understand it a little bit, you take one derivative of this, the skew-symmetric part of the gradient of u. It's called the vorticity, and it obeys an equation that's not purely transport, but there is another term here. It has a geometric meaning, but this term is called the stretching term. Conservation of energy, but the vortex lines, which are the lines tangent to this vector field omega, are carried by the flow, and that is written as a commutation between the advection derivative, the material derivative, and derivative along the vortex line. These 2 operations commute. So if you are a vortex line initially and you move it, transported it, you are a vortex line again. And because omega is kind of like gradient u, and you hear C omega times gradient u, you suspect the possibility of blow up. That has been going on for 30, 40 years. That suspicion is still a suspicion. And so it's an open problem. As I said, when we do regularity theory, we try to find the quantity that, if controlled, will give us regularity. And this is done here by the BKM theorem. The BKM theorem says that you need to control the maximum. So BKM is this, Biel-Kato-Maida. So this is omega. It's one gradient. L infinity means the maximum norm. So if the time integral of the maximum norm, which is a nice non-dimensional quantity, is finite, and if you happen to start with nice initial data, you'll be nice forever. So you don't need to control more than one derivative, and that derivative in L infinity in space, maximum in space, integrated in time. So that's the kind of sufficient conditions that I'm talking about, finite conditions. These conditions guarantee smoothness. They guarantee also uniqueness of solutions, although here we don't have weak solutions. So in addition to that, there is another property, which is a very nice property that is easily explained. And this is called geometric depletion of nonlinearity. What happens here is that in 2 dimensions, this term drops out. And it drops out because in 2 dimensions, if the flow is parallel, vorticity point in the same direction perpendicular to the motion, and this term drops out. Therefore, if this term is not there, this is pure advection, pure transport, like the equation for theta, doesn't change magnitude, doesn't add, doesn't subtract magnitude. So all of a sudden, the Biel-Kato-Maida is automatically satisfied because the magnitude is conserved. It's actually even in time, the supremum is finite. So in 3 dimensions, you have a local depletion, meaning that in 3 dimensions, it's no longer true that the vorticity points in only one direction. However, if the vorticity direction field is coherent, so for instance, suppose that it is smooth, suppose it's Lipschitz, suppose the vorticity doesn't jump from one direction to another, then you have a depletion of nonlinearity. So then you have regularity, not at the level of the derivative, but at the level of the velocity. Or for instance, for Navier-Stokes, you have regularity then. So why did I put this? Because I'm going to give you the analogies with the SQG. The analog of the vorticity is the rotated vector of the rotated gradient of theta, which is simply tangent to the theta levels of theta. So the levels of theta, therefore, are lines frozen in the flow. If you are on a certain level, theta equals 5, later on you're going to be on theta equals 5 as well if you follow the flow. The same commutation as before, the kinetic energy is conserved, the same equation, transport plus the stretching term, the same blow-up problem that's open, but in 2D, the same BKM with replacing omega by the gradient of theta in L infinity, and the same depletion of nonlinearity. So if the local isosets are really well, nicely organized, there is no blow-up. Okay, so purely geometry determines blow-up. So we're going to talk about dissipative SQG. Why? Because essentially we don't know how to do the inviscid one. Okay, so let's add some dissipation, and the dissipation is of the form lambda 2ds. And lambda is square root of the Laplacian. Lambda is the notation of Zygmunt. And in Fourier, that means I multiply by absolute value of k. And if I have an s, it's absolute value of k to the power s. And that obviously is going to be some sort of a damping that depends on wave number. So if s is larger than 1, I have here more than one derivative. The dissipation dominates. You have global regularity. And from the point of view of people who want to flex their muscles, it's too easy. Okay? If s is less than 1, this is super critical. It's dominated by the inviscid problem. It's open. it's difficult. If S is 1, it's critical in the sense of Goldilocks. Okay? It's just right. Okay? So now, for burgers, you replace this not with u being given by some relation to theta, but rather instead of this, you say u is theta. It's a scalar equation in, let's say, 1D. Then the criticality is real. So, okay, the word critical has been abused a lot in PDEs, and you'll hear a lot of criticalities that are in the sense of Goldilocks, and the sense of Goldilocks changes with time, because maybe we learn a new trick or we learn something new about the equation, and all of a sudden what was supercritical, because we didn't know how to do it, all of a sudden is subcritical because we know how to do it, because there is another conserved quantity that I didn't know about. So the case of Burger's equation says that indeed this intuition that if I pass from a semi-linear equation to a quasi-linear equation, when you do that, when S equals 1, actually at that point what happens is that you do have regularity. This is, I'm going to talk about that. But below that, when you're supercritical, you do blow up. So Burger's, which we know forms shock. Burger's with supercritical blows up. And with critical is regular. Okay, so that is the heart, the Goldilocks problem, which I'm going to talk about, which is really where the fun is how come when S equals 1, I can prove global regularity. So a little bit about lambda, because maybe for some people at first it looks like they don't know about this lambda, but in reality they do. Because if you exponentiate lambda, you get convolution with the Poisson kernel. So lambda of f is the derivative of this f, the exponentiation, with respect to this variable, artificial variable I introduced here, t. That's positive. So f is simply the harmonic extension in the upper half plane. So lambda, Laplacian f is 0. F equals little f on the boundary at t equals 0. And therefore, because minus ddt is the external normal to the upper half plane, lambda is the Dirichlet to Neumann map. Takes you from the Dirichlet data, you solve Laplace, look at the normal derivative, that's lambda. Okay? Very familiar, actually. And because of the Poisson integral, very familiar. This perhaps is less familiar to some people. There is a formula for lambda that looks horrible. And it's the basis of everything, actually. So if I want to compute lambda of f at x, I take f of x, I subtract f of y, divide by x minus y to d plus 1, and integrate in d dimensions. All right? This is violently singular at x equals y. Okay? So you have to actually, it's a principal value, you have to subtract not only the first part, f prime, but that vanishes, so you can go to second order. Okay? Otherwise, this doesn't make sense. So you need f smooth. So here is what's the BKM for this problem is much milder. So instead of talking about gradients of theta, I need theta to be Hölder continuous. So here is the result. It's a result with my former student, Professor Jahong, which is a professor now, from 09. So you take, this is SQG, this is u equals r perp theta, transport it, and it can be supercritical, lambda to the s, and s can be less than 1. You ask yourself, when do I know that if I start smooth, I stay smooth? Okay? And the statement is that if I take a solution that's actually a Lorentz solution, something that you can construct always, a weak solution, then if you know that it is C delta, with this delta being larger than 1 minus S, this is S, then you are regular. So in the critical case, S is 1, so you need any delta. Any little bit of Hölder continuity, you are home. Okay? So the game is, can I produce Hölder continuity out of nothing? And I want maybe to mention, okay, so there is a result by Vlad Vikol, who's my collaborator, and Luis Silvestre, who's an assistant professor who's promoted in Chicago. So this is a Chicago result. Like this. imagine that I put here a u like it was before, but it's not related to theta anymore. I'm free to put a u. So I have a linear equation. Then the statement is that there are solutions of linear equations with lambda to the s and with velocities that are 1 minus s, and they lose continuity in finite time. So it is sharp in the sense that I required delta larger than 1 minus s, and I couldn't require delta equals 1 minus s for linear equations. Could be true for nonlinear equations because there is an initial relation between u and theta.
Could you please explain what is a Lorentz weak solution for this equation?
So the statement, I didn't write it. So for weak solutions here, you can imagine for a second what happens, what is given by nature to you for free. You can multiply by theta, integrate by parts, and then this guy dies. It's divergence free, so u dot grad theta times theta integrated gives me divergence of u times theta squared. Divergence of u is 0. That's 0. So I get a conservation, I get this balance. I get ddt of integral of theta squared with 1/2 dx. And then here I have a 0. And here I have this guy, which I'm going to write down simply like theta s over 2 squared. Okay, so this will have this has s derivatives in it. If I multiply by theta, I can take half of those s derivatives and integrate by parts. So I have s over 2 derivatives, okay? Homogeneous space here, so doesn't matter. So I have this information for free. And with this information for free, you can form actually some solutions, quote unquote. So that means there will be functions which have bounded L2 norm and square integrable hs over 2 norm, and those are the Lorentz solutions. We can actually construct this as a result of my former student Serge Reznik, that even if you have no dissipation, there are L2 weak solutions. It's a very special case. So the nonlinearity is very special. You can actually construct L2 weak solutions, which is not the case for Navier-Stokes. So for Euler, sorry. So this is a sharp result, the for linear equations. So the Goldilocks result. There is, for small data in L infinity is, you will see it's a conserved space. It's if you start in L infinity, you will always stay in L infinity, bounded, in other words. So if you are small initially, you stay small forever, and you can prove relatively easily that you are good forever. For large data, there are 4 different methods and 4 results. So the original one is Kiselev, Nazarov, and Volberg. They are from around 2007. And they invented, this is a beautiful idea, amazing idea. They invented a maximal, an ad hoc modulus of continuity that is invariant under the equation. And so you start initial data that have this modulus of continuity, and then later on you prove that it is preserved. And this modulus of continuity actually near 0 tells you Lipschitz, tells you more than the Hölder that you need. You need any little bit of Hölder, you're done, and this gives you actually almost, it gives you s equals 1. Another proof around the same time and independently is using the Di Giorgi strategy of zooming in, and then L2, which is something that you are given like in that thing for free. Then you promote the L2 by zooming in to L infinity to boundedness, and then the hard thing is to promote from L infinity to C alpha, and they do this in a very complicated way by essentially using this Dirichlet to Neumann idea, going in an additional dimension and doing that. Kiselev and Nazarov tried to do a harmonic analysis proof that's very nice, but I don't want to talk about it, with co-evolving molecules. It's harmonic analysis. And we, with Vlad Vikol, I never understood where is it. So let me, essentially, I'd like to emphasize the fact that you are looking at an equation that has first order derivative damping fighting u dot grad theta, which is also first order derivative, but it's quadratic, it's big. So why is it the same one derivative beat another one derivative multiplied by something big. If it was an ODE, it would never happen. Okay? So, and in all these proofs, you don't see where the beating is. You can verify that this thing is invariant, but you don't see where was it the dissipation beat the nonlinearity. And in the George strategies, forget about it. You don't understand where is it at the end that you're actually winning. So I want to show you where, and that is based on this nonlinear maximum principle. And I'm not going to talk about the stability of only small shocks. So nonlinear maximum principle for linear operators. I mean, I think that people should object already. How can I have something nonlinear for a linear operator? So here it is. I'm going to write, I hesitated to do this, but it looks like it's a kind of an error, but it's calligraphically it's nicer. So suppose I have a directional derivative, if you wish, of a function, and I take a place where it attains its maximum. And that's called gradient f in infinity. Then there is a constant depending on dimensional space only, so that if I apply lambda to the gradient and look at the maximum, is larger than the gradient square in L infinity divided by f in L infinity. So it has the correct scaling. Let me give you an S. So there was a Cordova maximum principle that says that this is positive at the maximum. So it's a very useful information, and I'm going to show you a little bit how it works. So if you have S, you get 1 plus S divided by f in L infinity. So it is obviously dimensionally correct. I have 1f, I have 1f. I have 1 plus S derivative, I have 1 plus S derivative. Okay? But it's nonlinear if I have information about L infinity. These are equations that are moving stuff around. They don't create, they don't destroy stuff. So if I know how much stuff I had with beginning, I have the same amount. So L infinity is conserved. It's free for me. And I'm interested in gradients. So this is really the reason why it will beat. So let's do one more comment. I'd like this for S. It's true for all S between 0 and 2. The constant goes to 0 when S equals 2, so it's not true for the Laplacian. Okay? So there are variants. If you happen to know C alpha, one of these things, you get more nonlinearity. If you know almost alpha equals 1, you get almost infinity here. So equations that conserve C alpha, there are not many. Once you are there, you are in good shape anyway. If you know less, which is often the case, Navier-Stokes, for instance, then you get still nonlinearity. The less you get, so if you know, in the end, if your information is p equals 1, you get something. Okay? This is very important, but you probably don't understand why. So let me explain what happens. Suppose I have an evolution equation for a function I differentiate it, and I call g the derivative, and I want to control the evolution of that. Just like I took here the quadratic part and integrated by parts, I would like to do that for the derivative. Okay, g is the derivative, so I will end up by having a quantity like g times lambda s to the g. And that quantity is larger than lambda s of g squared plus a very healthy dissipative term, which is very singular, therefore very good because it has the right sign. Okay? So for instance, in the thing, I wrote this thing again with gradients, okay? So the quadratic expression that appears there is larger than, as we expect, gradient of f to 2 plus s. So imagine in your head that you are doing this SQG equation. It has s equals 1. I take a derivative. It was quadratic, so I have now gradients squared. I multiply by 1, gradient, because I do this quadratic expression, I get cubes. This gives me cubes also. Okay, s equals 1 gives me cubes. So this is pointwise. In other words, if I knew that this is small, you are already having a larger dissipation than the nonlinearity. So the critical case is when I don't know that this is small. So the small data result in L infinity, for instance, falls out of this nonlinear maximum principle automatically. This is true in general with much more complicated operators, and you'll see in works of Caffarelli and Vasseur, more complicated equations of this type, and all this falls out, the results will fall out from this nonlinear maximum principle. So all you need is K, the singularity, to look a little bit like the singularity D plus S in, so in other words, it has to have non-integrable singularity at 0 and integrable at infinity. This is one more variant that I want to show you. If I take, because I will have to take finite differences, and I look at my quadratic expression that I will get by trying to get L2 bounds for finite differences, as it were, then I get a quadratic expression. I get this thing is the equation. I'll show you in a second. And you get this beautiful, powerful expression with 1 over h's to the power s down, which is, again, extremely singular, therefore extremely good because it is with the right sign. So now let me, I have kind of like 5 minutes. I'm going to state 2 results, and I may give you an idea of the proof, or the meat of the proof. So the 2 results are the following. This is the same equation, but I put D instead of lambda because I allow also, here it is, D has also 1. Okay, so there is damping, 0 mode damping, friction, plus lambda. Okay? So the result is, remember the Kolmogorov thing? The fact that you can take averages, multiply by the coefficient of viscosity, let it to 0. In the case of viscous, damped, driven SQG, there is no anomalous dissipation of energy, and this is a new result. And then the other result that I want to mention, you do for periodic, the same story. Now I don't need to add damping. It's only pure lambda. And we work in H1. Doesn't really matter. The result is, let me put all the thing. The result is that there exists a global attractor, and it has finite dimensions, finite fractal dimension. And as smooth as the force is breaking. So the right-hand side is C infinity. The thing is formed with smooth functions. Now, this is, again, non-trivial to some extent because you need to know bounds that are independent of the initial data in order. You need something called attracting sets. You need to, in the end, to get into regions that are depending only on your forcing. And all the proofs that we had so far remembered the initial data because they were maximum principle based proofs.
Can I ask a question about that? Previous statement, yeah. How does this fractal dimension, the Lyapunov dimension, depend on the parameters in the problem?
So there are some bounds, right? So there's the, okay.
How big is this dimension?
In terms of what? Because I have a forcing and I didn't even put a parameter in front of. So the answer to this is that this is a very new result. So I can give you some answers in terms of norms of the force and 1 over kappa, if you put a kappa here. So it depends to some algebraic power, but we haven't worked. It's not like Navier-Stokes where we had 20 years to finish and get the best kind of results. Okay, so it's just relatively new. So it will be. It's not exponential in the parameters. It's algebraic. So it will depend on. In this way, I wrote it here. It depends only on f and a couple of derivatives of f in L2. Okay. So let me finish with the main result here, which is a new global regularity for SQG. And it says that in the case of the forcing, if you wait enough, then you get bounds in L infinity and in a particular C alpha where the alpha and the bounds are independent on initial data. Because that's what you need for the attractors. If you wait enough, you're going to get yourself in a region of space that is dominated by your forcing alone and parameters if you have a viscosity, but they forget the initial data. Okay, so there's absorbing sets. And very non-trivial result because all the proofs so far were doing maximum principle, you never forget your initial data. You're never bigger than what you were at time 0. But you need something to be able to say, I have a damping. Okay? So I'm not going to, there is a damping in L infinity, and this is non-trivial because there is a constant that's independent on P, but I'm not going to talk about it. Let me give you the main thing. Okay, so this is 2 slides and the conclusion slide. So this is really, this horrible thing here is the main thing. So you take your equation and you take a finite difference. When you take a finite difference, you get the equation on the finite difference. You get an additional term, which is the finite difference of the advection, dotted into a gradient in the parameter that you translated with. So this has a maximum principle by itself, because you just move stuff, or damp stuff. You never add stuff. So if initially I had a ramp, unfortunately the maximum of that is, like if I have a segment, then the finite difference maximum is 1. And it doesn't tell me anything about Hölder continuity at all. I would like to stay close to h equals very small. So, but we can now mess with it, divide by h to 2 alpha, I don't know yet what alpha, and try to imitate this conservation. Well, I cannot, because now this doesn't depend on h, this doesn't depend on h, this doesn't depend on, but this will differentiate my h to the alpha. So I pick up an alpha times delta h of u and a hefty h to minus 1. Remember, my dissipation had an a, I told you that beautiful h minus 1. These are exactly of the same order. So if your Berger's equation, maybe I should stop with that. If your Berger's equation, your u was theta, these terms would be exactly the same. You can pick alpha small enough. If you pick alpha smaller than the 1 over the L infinity norm of your dude, you're done with this term. The forcing is really not very nice, and you're done. For SQG, u is not theta, is related by a linear relation. So this is the philosophy. U is like theta, alpha small, hide the bad cubic term. Okay? Now, and obtain an ODE for the maximum, which is non-trivial. So for SQG with work, you remember that you had this DH. DH was larger than this, so I keep half of it. And with work, you can obtain a bound. So at the end, hiding the cubic term requires alpha times theta L infinity to be small. And you can do that because you know theta L infinity is controlled from the beginning, and actually the other argument that if you wait, it will be small. So there's a new proof for regularity using the nonlinear maximum principle, obtaining directly without iteration the de Giorgi improvement from L infinity to C alpha, just like that. If you ever saw a proof of the de Giorgi principle, it's painful. Okay? I don't think this is painful, but of course, it's a matter of being used to it. Okay, once this is obtained, then you go to higher things and you can get the attractor. Okay? So I'm going to finish with my conclusions. That's one form of writing the maximum principle, and I thank you very much.
Other questions? So when you say that you have no anomalous dissipation, as I recall, Kolmogorov uses constancy of this dissipation to get the k to the minus 5/3 law for turbulence. Do you have any spectral information about the system?
There is spectral information, and it is actually, this is an older story. So there is a k to minus 1 that was observed numerically. I mean, we don't have theorems about it. And it's related to things that were observed by, so these are older stories, actually I didn't review them recently, by Sweeney in his lab. So this has something to do with rotating and with bottom friction. There is a damping term. So it's a different mechanism. So this but it is not present there if, in the case, remember, I have a damping term and critical dissipation. So I don't know for the what the exact spectrum for the critically dissipated case. So this is for SQG, the K minus 1.
Is the nonlinear maximum principle familiar in the case when lambda coincides with the directly Neumann operator?
You mean with
When S is a half or something?
well, S equals 1 is directly to Neumann. So that's, yeah, it goes between 0 and 2 for all of them.
So is it familiar in some way in that classical case?
Familiar? No, I don't think so.
It's not an existing result.
No. No, this is new. It appeared in GAFA in 12. The reason why it is probably not familiar is that it's a little unusual. You're asking, it's a shape kind of thing, and you're assuming information of a primitive, of antiderivative of the function. And why would have people looked at that? I don't know. We know why we're looking at it.
But in the case when it's a directly Neumann operator, in some sense the operator is local as well as being global, isn't it? If you look at it in a higher dimension.
If you it is.
Higher dimension, it becomes a local problem.
Right. Well, the problem is, it's local in the sense that you look at the Laplace's equation with some boundary condition. The Laplace equation is local, but you're looking at the boundary transmission from that. No, I don't. No. So this is new again because of the way it's formulated. It has something to do with this gain with respect to the derivative. So I have information. Yeah. So it's extraordinarily useful. It's versatile. In other words, I thought you were asking me if there is one for curved boundaries. So, okay, so there must be. I mean, actually, as I said, there are all these 4 integral operators with kernels that have this kind of singularity. You don't need all you need is that is extremely singular at near the point where you're computing, and the singularity is integrable away.
More questions? Thank you, Peter.